So my name is Kevin Liu. It's from China University of Petroleum. So the talk today I'm going to give is a geomorphologic evolution of the Northern Tibetan Plateau during the Quaternary. I will mainly focus on the tectonic and climate coupling effect using landscape modeling technique to study this region. Professor Ha gave an excellent talk just before me, so I hope my talk will give you some insight for your work in Pakistan and other places. First of all, I would like to just to acknowledge a few people. Okay, this is actually the work from my PhD student, Weijing Liu. So the work is being published in the International Journal of Interpretation. I would also like to thank my former colleagues and also a lecturer from Sydney University, Dr. Tristan Salish, who actually introduced us to this pyBadlands computer program. He actually designed the whole program, and it's now an open source software that anyone can get access to it. So also funding from China Academy of Sciences and also the National Natural Science Foundation of China. So in this talk, I will just divide into 5 parts. I will first talk about the background of my research area. So everyone knows that the Qinghai or Tibetan Plateau is probably currently the largest and the highest plateau in the world. Okay, also with the thickest crust of 70 kilometers. It's often referred to as the roof of the world, as you can see from this image. So from here, we know it's a very thick crust, and also the Mount Everest is right in this region. So we all know that it's the geodynamic movement in this area, actually probably the most important global geoscience event in the Cenozoic from the Indian plate collide with the Eurasian plate. Also, because this collision and also the geodynamic setting, it has a profound impact on the climate and the environmental changes in Asia or the entire northern hemisphere. We know the monsoon and the trade wind in the Asian countries, it's partly because of the uplift of the Tibetan Plateau and also the mountains within it. So the basin I'm going to talk about today is the Qaidam Basin right here in the northern Tibetan Plateau. It's a intramountain basins or intermountain basins. So at an elevation of around 2,600 meters to 3,000 meters. So the reason we choose this basin to model is because it is an enclosed basin. So all the sediment from the surrounding basin dump into the basin, and we can really work out the mass balance. We know how much sediment gets in. It always has been preserved within the basin. So this is one of the reasons we choose to model the Qaidam Basin in the northern Tibetan Plateau. So first, it's in the northern part of Tibetan Plateau, right in this area. The size of the basin is around 120,000 square kilometers. It's quite high, as I mentioned, that's around 3,000 meters above sea level. There are mountain ranges surrounding this basin, including to the west, the Altai Mountains, to the north, the Qaidam Mountains, and to the south is the Eastern Quinlan Mountains. So it's all surrounded by these high-rise mountains in this area. So we're going to do a tectonic evolution of the Quaternary based on numerical modeling. So here are some shots from the Qaidam Basin. You see the landscape, it's a rugged terrain, and also there are lots of planation surfaces, river terraces that can be used for dating the uplift of the plateau and also the surrounding mountains. So we know it's the largest Cenozoic terrestrial intermountain basin in the world at the moment. So it is really ideal for understand the mass balance of sediment source sink study in this region. Also, it's good for studying the coupling between tectonics and the climate interaction for sediment evolution. Because we know it's a very intimate relationship between climate and tectonic in this region, and it affects the whole entire Asian climate and also perhaps the northern hemisphere. So there are lots of studies in this region. We know particularly on the sediment evolution or structural kinetics process, but among all these studies, sometimes they only focus on particularly a section, like a Western Qaidam Basin, or also eastern part or northern part. They never been a comprehensive study of the entire basin. The other issues in this previous studies is most of the work has been qualitative and conceptual. So in our studies, we want to study the entire basin as an entity from the viewpoint from a source sink and also from a quantitative approach. We want to know how much sediment contribution from each sector and what the impact of climate or tectonics on the sedimentation and also the basin evolution. So just to give a background, there are currently two viewpoints on the Qinghai-Tibetan Plateau. The uplift timing, one group believes that the area has been attained to its present height in the middle Miocene or even earlier. So this is primarily based on isotope geochronology, also published geochronology and the plant fossils. So this is a viewpoint held by one group of people, such as Clark in his 2010 paper, and a few other peoples, and Spencer 2003. So this is one group of people's view. But on the other hand, the second group of people, again, this Clark 210 and also 2017, they believe the plateau only reached its present height in the Quaternary. So we want to test this a controversy. When did the plateau reach its current height? So this group view based on a number of megafaunas like rhinos, elephant, giraffe faunas found dated in this region. So they believe the climate setting during even 10,000 around certain regions is still livable for big animals. So they believe the uplift of the entire area is quite late. So this of the scenario we want to test in our simulation. So this is some short of the big faunas found in this region. We talk about megafaunas. So the key issues we want to address in our study is include, we basically want to build or construct a tectonic evolution model for the entire basin. We call it 120,000 square kilometers. We want to check the timing of the uplift because there are controversies at the moment. So one group saying it's very early, the other think it's in the Quaternary. Thirdly, we want to understand the factor that's controlling sedimentation, whether it's the tectonics alone or climate or the coupling of both control the sedimentation within the basin. Finally, not least, we want to understand and quantify the source to sink in this region, because as I mentioned, that it's an enclosed basin, it's got sediment supply from 3 mountains ranges. So you want to understand what the sediment contribution from each range. So I'm going to talk about the method, spend some time on the method. So I think this pyBadlands is basically short for basin and landscape dynamics. Okay, so I use the red for PY essentially as a parsing algorithm based, computing language based. It's a parsing based open source and parallel computing landscape modeling in a program that can simulate both erosion and deposition. This is actually the program created by one of my former colleagues called Tibetan Plateau, that can be used to investigate drainage evolution over in a continental scale up to hundreds of millions of years. And it can also be used for a small scale, short-term landscape evolution. I'm going to show you quite a few examples. So essentially, the program can simulate the landscape uplifting, denudation, and deposition by considering a number of factors and processes, including hill slope using simple creep law, overland flows for stream power using stream power law, and the flux apostasy, the tectonic loading, and also the sediment compaction. So in this program we used for the simulation, basically contain a number of terms, like including the continuity of mass, the erosive power of the water flow, diffusion process, and tectonic. So this is essentially the key equation within the Badlands program that we use. So this is the author of the program is my former colleagues from CSIRO and now in Sydney University, Tibetan Plateau. So here to create this program, and currently it's open source, being widely used by many people in different parts of the world, including my students. And actually, lately, someone from University UT Austin just published one paper in geology using Badlands to simulate for simulation. So this program, by simulate the landscape evolution and sedimentation, so we can we can do a number of things using the following example to show you. Okay, first, for this program to use, we need to use the the Jupyter environment. So it's script based. It's on the internet. We can access to the open source network, open source code. The Jupyter notebook basically also an open source web-based application, so which allow you to create a shared document that contain live code, equations, visualization, and narrative text, include data transformation, numerical simulation, modeling, data manipulation and visualization, even machine learning, and much more. So it's an excellent open source environment. We use this often in our research. So in this environment, we can start the Badlands program, which is also an open source program, and set up our model and running the program. So when we run the program, it has some general structures. It's based on the XML input file format. So we can set up the program by setting the grade, time, stratus, sea level, tectonics, precipitation, surface process, erodibility, hill slope process, waves, if we do a marine setting, and carbonate modeling, fracture aesthetic, and then output. So this is actually the structure of this module. So, for example, just for the grid structure, it's everything is working in the grid. You can use XYZ data to input the low left corner to the upper corner. This is north to the upper is north. So we can set up all our input profile based on this format, this grid format. So this workflow, we can set up our program using discrete input, such like tectonic topography, sea levels, dynamic topography, and also on the other hand, we can also do some statistical distribution on the initial topography, erodibility coefficient, and precipitation. We can do a continental scale landscape evolution model, or you do a local scale modeling. But for all this work, we need to do a model validation using present-day topography. As in our case, we use the Google Earth derived DM model, or counter rivers and sediment thickness. So we have to validate our model before we accept as the final reasonable model. Okay. Well, once we set up model, then we need to do the simulation, or we call processing. In one part, we call the morphometric processing. Basically refer to quantitative description analysis of the produced badland surfaces, which can be used for a particular kind of landscape, or to a drainage basin and a larger region. So in this geomorphic attribute can be extracted, including the gradient, so the magnitude of maximum gradient, horizontal curvature, vertical curvature, aspect, this basic direct maximum gradient, and discharge. So we can get all this information from the model once we complete it. So this is the morphometric analysis using in the badland simulation. We can see this precipitation and also the orogenic precipitation with time. So this is the process in this model. Okay, just to take example, this one we using the stratigraphic analysis. Once now this options are turned on, the badland can try to produce a landscape and also sediment deposition. And in this one, we have this one. It's the dark brown is sedimentation, and the blue part is denudation. Okay, we can see this. This is running 30 million years deposition. You can see this sea level up and down, and also interact with the drainage, sediment erosion, and deposition. This work has been done by a student with the Tibetan Salish in Sydney University. Once we done this, we can do a cross section to analyze this quantitatively of the stratigraphy. All this is done using peer review within also open source code. We use this to realize the program and the simulation result. So for the stratigraphic record, it not only can do the space domain, also can do a time domain, doing the Wheeler diagram in 3D. So we can build the landscape and stratigraphic record in space domain, and also in the time domain in 3D. So this is quite useful, as quite often we need to know the sedimentation rate, the deposition and denudation, and the missing section in a basin sequence. So this is quite useful for quantitative analysis like basin modeling. We need to work out exactly how much sediment has been denudated or missing at a certain unconformity. So this is an excellent program for us to use. Also, it can be used to reproduce the discharge of landscape. This is in southeastern part of Australia, and also the catchment characteristics to complete the source-to-sink analysis of sediment. That's why we use this for the Qaidam Basin to basically quantify the source-to-sink, the sediment contribution from particular part of the basin, and also to ground truth the exhumation history, and also it can be applied to lots of other places as well. So this is another example. We use it to model the Australian continental margin, highland formation. In one of these, the model is capable of simulating what we call the hill slope process, like using diffusion law, the fluvial erosion using stream power law, sediment transport using sediment flux conservation, and deposition in a depression area, as well as acidic fracture and heterogeneous lithosphere. So this can be all modeled within this program. So it can be used to quantify the geomorphic and sensory response to spatial and temporal varying tectonic and climate force, particularly with the precipitation at sea level. So this is the part that we use in the Qaidam Basin simulation. So we really want to understand the geomorphic and sensory response to the uplift of Tibetan Plateau and to the glaciation and interglaciation in the region. So this example using PyBadlands for regional scale model, again in the Southern Australia, we can see this very short period from only 40,000 years. So you can see the change of the shoreline and the denudation patterns for this region. However, this is a better example. This is a very short-term simulation. We talk about from 2020 to 2,500. It's only 480 years change. This is the northern New South Wales in the eastern coast of Australia. We call it the Tweed Head. It's just near the border between New South Wales and Queensland. It's a summer resort town. There are lots of huge people living there, but the area is subject to coastline erosion. So by doing this, we can inform the government or the people that the land with a certain sea level rise, what's going to happen with your coastline and also the living area. This is a large-scale simulation of the almost entire Australia. You can see this. We talk about in 100 million years and 1,000 kilometers landscape. So basically, this project started by Tibetan Salish in Sydney. We try to model sea level changes and also the deep earth mantle convection, coastline evolution, erosion of sedimentation, the river network evolution, also the erodibility and rainfall. So this we are talking about millions of years and also 1,000 kilometers across, involve the deep earth process and surface process. So the coupling between the climate, tectonics, and also sea level changes. So you can see this, the drainage pattern changes. This over hundreds of million years. So this program can be powerful for doing the work we need to address our issues. Also, it can be used to do modeling of bare reefs, coral reefs growth. We talk about only 10,000 years growth in the Holocene or in the late Quaternary. See the shoreline changes and the Australia Great Barrier Reef in the northeastern Australia. We can see these changes using this program by influence sea level and the growth of the coral reef and the sedimentation within it. Also, we talk about the sloping process. These are the slide into the basin from the steep slope. So currently, this program has been coupled with the geoplate and other program to do evaluate the deep earth process. We talk about the tectonic and mantle conversion on the basin evolution. So by combining G-plate and other sitcom and this simulated dynamic topography, we can coupling the bedland during the initial to simulate the topographic evolution, erodibility, precipitation, and sea level. Using this process, we can just link the surface process to deep process. So this is the workflow. Actually, from G-plate, sitcom, we get the large-scale dynamic topography of the continent. Then by using incorporate with bedland simulation, we can simulate the precipitation, paleotopography, sediment thickness, the paleo environment, and also we talk about denudation rate and sea level changes. So all this you can, if you are interested in, there is a link here. This is the Earthbite group in Sydney University with Dieter Müller as the group leader, and also Tristan Selisch is the one of these lecturers in this group. So you can see lots of information within this website. Okay, www.earthbite.org. Now we can talk about our model setup. So as I mentioned before, so the Qaidam Basin is in northern Tibetan Plateau. It's an area of intensive study by many peoples. But the big issue there is people most focus on a particular part doing qualitative and conceptual studies. For us, we want to study the entire basin right here. So we talk about 120,000 square kilometers basin surrounded by 3 big mountain ranges. So we want to use bedland to quantitatively simulate the denudation and deposition of the Qaidam Basin and surrounding ranges. To quantify the contribution of the source to sink, because the Qaidam Basin is an enclosed basin in the Quaternary, so there is no sediment out or or in. So basically, all the sediment is dumped from the mountain ranges and being preserved within the basin. So this provides an ideal case study to quantify the source to sink contribution. So let's look at the Quaternary stratigraphy. The entire basin contains up to 3,000 meters Quaternary sediment. It's a lot of sediment. It's many mudstone and sandstone and shale with certain part of evaporite, halite. Sometimes we have some carbonaceous mudstone in there, but mainly it's lacustrine sediment. It can be a saline, lacustrine, fluvial, deltaic sediment. In this sequence, what we can see, there are 4 tectonic uplifts from roughly from 2.5 million years. We call the Qingzang movement B. And then at around 1.7 million years, there is a tectonic uplift of the Qingzang movement C. at roughly around 1.2 million years, there is a Qinghai movement, and finally at around 150,000 years, this is the Gonghe movement, the last tectonic movement. So basically, in this diagram, we can see a few lines. This is the dashed line here is the uplift of Tibetan Plateau. Okay, so this is the marine isotope record, MRS, and this evolution. So we see the Tibetan Plateau starts from 1.8 kilometers all the way to the present around 3 or over 3 kilometers. For this dashed dotted line, it's the uplift of the main mountain peaks. I start from around 2.5 or 2.7 kilometers to roughly over 4,000 meters. So you can see that over the very short period of 2.5 million years, there is a significant amount of uplift in this region, in the Tibetan Plateau and in the surrounding mountain ranges. So this actually we have the magnetic age, paramagnetic age, and also these marine isotope stages from stage 2 all the way to stage 98. So this provides very good control on the timing of the uplift. Also in the diagram, you can see this is actually the glaciation. This stands for the glaciation. This is the ice age of Tibetan Plateau. It starts from around 0.8 million years. We start to see ice stages in the Tibetan Plateau during the various stage. Okay. So this actually forms the basis for our modeling. So we know our model starts from 2.5 million years all the way to present. We want to incorporate the tectonic uplift, climate. We're using the marine isotope record using stage 1 to 98, and with the timing we're using PaleoMag. We also consider other information in this region. So to build the model, we need to understand the paleotopography. So this is the cross section from right here in the northeastern part of the Tibetan Plateau. We got one profile here from Hezur to Lixia. We can see the uplift of the plateau basically is a metal plate movement and this spheric tectonic deformation, because the cladding of India plate with the Eurasian plate causing tectonics uplift and warping. So basically we need to use integrated geomorphological and paleontological evidence so to reconstruct the paleotopography or paleogeography to build our initial surface. Also, we're using data published by other people. For example, this is Drew in 2003, identified 5 tectonic uplift in this region from tectonic movement 1 to 5. Basically, it's based on the sedimentary analysis in a number of boreholes in this region. We know the Northern Tibetan Plateau basically experienced 4 phases of tectonic uplift during the Quaternary. Okay, as I mentioned in the early slide, the Qaidam movement B is from 2.5 to 2.28 million years. Movement C from 1.94 to 1.66 million years, while the Qinghai movement is between 1.2 to 0.6 million years. And the last tectonic uplift is the Gonghe movement, around 150,000 to 90,000 years. So this is information we need to build into our model, conceptual model before our simulation. So also, based on other published information, including the elevation of the Tibetan Plateau, using this sign over from 80 million years to present, this has been well established. Also, the mountain peaks of surrounding mountains. So on that, we also build upon the high frequency climate curves using, so this is the glaciation, okay? This is elevation of the plateau, the surface, and so this is the high resolution, high frequency climate changes in this part. So we can actually correlate quite well with the 4 tectonic uplift stage from Qingdao movement B, C, and the Qinghai movement and the Qinghai movement quite well. So for the tectonic movement, which is also a parameter required for the simulation input, we actually discuss separately for different mountain ranges. This is the Altai Mountains right in the western part of the Qaidam Basin. So it's underwent rapid uplift in the early Pleistocene, as indicated by the rapid sedimentary deposition rate. So this deposition rate suggests a rapid uplift of the Altai Mountains. Also, there are southern profile here, also shows there are 4 facial uplift in the Altai Mountain, as I mentioned, that from 15 million years, 8 million, 3.6 million. And the last uplift in the Altai Mountain is 2.5 million years. Paleomag data showing some more detailed tectonic uplift beginning around 3.6 million, and also identify the one at 2.5 million. Additionally, it's also identified the one at 1.1 million years and also 0.8 million years. So the Altai Mountain right here in the northwestern part of Tibetan Basin was uplifted and exposed after the Miocene. It was further uplifted from 2.6 to 2.1 million years and reached the present elevation in the late Pleistocene, around 250,000 years. So all this work based on the terrace, all the terraces on the Piedmont deposit and planation surface in this region. So let's go to the western Qinghai Mountain right here. So in this region, the plantation surfaces and the river terraces suggest that the landscape of the eastern Qinghai Mountains, which is the southern part of Qaidam Basin, was mainly formed by the Qinghai movement and the last Qinghai movement at 1.2 million years and 150,000 years, respectively. It's quite late. You can see, as compared with the Altai Mountains, this uplift is quite late. So for the western mountains, we also understand the large glaciers in the beginning of the Quaternary period actually occurred in the Pleistocene around 800,000 years. So this suggests the main peak of the Qinghai Mountains must be at least 4,000 meters around 800,000 years. So the last rapid uplift for the eastern Qinghai Mountains, we believe, occurred at around 800,000 years, based on thermochronological evidence in this region. There are huge amount of data in this region. Let's go to the southern Qaidam Mountain, which is the northern mountain ranges north of the Qaidam Basin, the last mountain ranges we talk about. So let's look at the snow lines. At the moment, from 450,000 years to 500,000 years. So the snow lines at around 3,500 meters. but at the present, the sea line is around 4,000 meters. So from the snow line changes, we can really understand the tectonic uplift in this region. Also based on this mountain peak and the plateau elevation. So we know the Chilean mountains began uplift on 3.6 million years, but later on experienced the Qingdao movement, B and C, and the Qinhuang and the Gonghe movement. So in this region, the Chilean mountain has experienced all the 4 tectonic movement in this region. So for the paleotopography, we're using the Google Earth DEM, but also at the same time we try to subtract the sediment deposit and to construct a synthetic paleo landscape to come based on all the studies I mentioned before. So based on hundreds of studies in this region. So we determine the uplift rate for the entire simulation from 2.5 to 2.8. We assign tectonic uplift rate, and also for each basin, for the Quaternary mountain, Argentine mountain, and the Chilean mountain. So we have this mountain range at a different uplift range based on published work. But this paleotopography is based on the DEM model. For the climate, we're using known ice ages, interglacial and glacial timing. We know the earliest Quaternary ice age in China is basically dated back to the Wangqing glaciation around 0.7 to 0.5 million years. This is the earliest known glacier in China. There are also 3 other glaciations. So basically present in the mountain ranges around the Qaidam Basin, including the Middle Pliocene. There is a period of glaciation, and also the late Middle Pliocene, and the last ice age right here in the late Pliocene. So we build up all this information into our model. So this is the summary of the climate curves we used for the simulation. So here we combined the 4 classical glaciation in the Quaternary with the marine isotope stages. Okay, so it's roughly from present date all the way to around 1 million years. So we know exactly the ice age and the interglacial and glacial period. So we build in this into the R model for simulation. So for this climate, we also refer to the present rainfall in the Qaidam Basin, and also assign a different rainfall for the different regions of the Quaternary mountains, the rainfall from the Argentine mountains, and rainfall for the Chilean mountains. So basically, we know the current annual rainfall in Qaidam Basin is quite low. It's very dry. It's only 20 millimeter to 400 millimeter per year. But the Eastern Quaternary mountains belong to a subpolar glacial zone with an annual precipitation of 500 to 1,000 millimeter. And the southern Chilean mountain is, and also the Argentine mountain here belong to a polar glacier with a much lower precipitation. So there's not much precipitation here. This region and Qaidam Basin also quite dry. We talking about 20 to 400 millimeters per year. So we're going to show the result here. So this is the modern area we talk about the entire basin, 852 kilometers by 400 23 kilometers with resolution of 3 kilometers. The modern duration is 2.5 million years. As you can see, we're using 250 layers display at every 10,000 years. And here you can see, I just want to draw attention, this is the Qaidam Basin. You can see the uplift rising of the mountain range and subsidence and sediment supply. This is the reddish, yellow reddish thick sediment deposition, and also the denudation. Let's run this again. I just want to draw attention to the mountain range denudation and the sediment supply basically only become pronounced at around 800,000 years. You can see this, all this in a drainage, catchment area, and sediment dumped into the basin. So this actually suggests now the climate actually have a big impact on the denudation of the sediment from mountain ranges and also the sediment within the Qaidam Basin. So let's have a look closely at the result. Just in a time slice from 2.4 million years also to present day. So this the elevation we can see here. This is from slice 1 is 2.4 million years. You can see this the initial evolution basically was there to main peaks around 1700 to 2500 from 2005 meters to 1700 meters. You can see this as we progress from slice 1 after the four tectonic uplifts we mentioned, like the Qionzang and the Kunhuang and also Gonghe. So the main peaks was raised to 5,000 meters and almost to there. And the basin center reached elevation of 3,000 meters at the end of Quaternary, and basically through a combined effect of tectonic uplift and subsidence. So this shows this profile right here. You can see the evolution of the Tibetan Basin and other part. And the final geomorphic patterns, what we call this one, with evolution basically vary around 2,000 to 3,000 meters right here. So the basin has been filled by the sediment dumped from the surrounding mountains and between the mountain peaks. So let's look at the sediment. This one we talk about the topography of the Qaidam Basin, and here we look at the sediment. Again, from slice 1 at 2.5 million years, we start of simulation to the final one at present day sediment. As I mentioned, this is the yellow and the reddish is the sediment thickness. So at the beginning, basically in the early Pliocene, the Altan, Quinlan, and Chilean mountains were uplifted quite violently, with most sediment supply from this Altan mountain. So after 1.5 million years, large amount of sediment was transported from the source area into the Qaidam Basin over long distance, and we accumulated roughly over 1,000 meters sediment by 1.5 million years. So after the Kunhuang movement, we talk about 1.2 to 0.6 million years. The plateau reached around 3,000 meters, and glacier began to develop in the Qinghai-Tibet Plateau. We have a glaciation roughly between these two. So at around 0.5 million years, the Tibetan Plateau into an interglacial period, when large amounts of melted water flow down the steep slope mountain and converge into the basin, deposit huge amount of sediment. So this is the sediment deposit during the interglacial period. So, well, how do we know whether our results are right or not? We need to compare. This is the elevation map with the present topography from Google Earth, and this is our model's topography. We can compare with the the legend here as quite comparable. So our simulation, the final topography and the current topography from Google Earth is quite similar. But in terms of sediment supply, sediment deposit, this aspect map of our simulated area in the Qaidam Basin, they compare with the known sediment thickness from boreholes and seismic. So again, it's quite comparable between the two. So our model clearly reproduce this basin sediment, also topography in both aspects. So now we're going to discuss. So we know, as I mentioned earlier, so one of the things we use the model is to try to work sort of think and quantify these things. From a simulation, we can quantitatively determine the contribution from sediment from the Tibetan mountains to the Qaidam Basin is only account for 14.37%. But roughly similar contribution from the northern ranges, the Qaidam Basin, is account for 42.95%, and from the eastern Quaternary mountain around 42.68%. So clearly, this have never been done before. So we know not only know exactly how much sediment has been dumped into the basin and the tectonic sedimentary evolution, but also we know the contribution from each provenance into this basin. So this is the good thing with the pyBadlands modeling. We know in any given seal, we know the sediment, the fate, and also the source to sink. So let's look at the other part. Well, if you look at the Qaidam Basin, we look at the deposition and also erosion. So this one, we use the time series from right from start of simulation 2.5 million years to present. It's a cumulative. Okay, what we see here, the red dot line is the maximum erosion because we have many seals in this basin. So this is the maximum, and this line represents the average, and the dashed line here is a quarter and three-quarter erosion. So basically, the average erosion is roughly in this line. But because of the variabilities, there are certain parts of the basin also got up to 800-meter erosion. Let's look at deposition. With this again, we use this average deposition. This is also cumulative. In this basin, on the average, we have 800-meter deposition, but in some parts we would have over 3,000-meter deposition. So it's big variabilities here. So in this basin, if you look at the erosion and denudation of different mountain sections, the Qaidam mountain is from the initial simulation to the end. So we see the erosion up to 200 on average, but it can be maximum up to 2,000 meters. For the deposition, because this area is intermountain basins, as the can got an initial deposition, then erosion. So, but on average, the deposition within the Qaidam mountain is only 100 meters because it's erosion areas, not deposition. The same thing would be true for the Tibetan mountain. The erosion, the maximum erosion up to 2,000 meters, but the average is around 400 meters. The deposition, again, on average, is only 100-meter deposition. For the Quaternary mountains, we can see the erosion, the maximum erosion up to 2,000 meters, but the average is 200 to 300 meters. For the deposition of Quaternary mountain, again, we can see it's roughly no more than 100-meter deposition within the mountain. So this is a summary chart I want to show. This I will probably spend a couple of minutes on this. So in this chart, I want to summarize the deposition of Qaidam Basin over time from 2.5 million all the way to present. I will like to draw your particular attention to this region, where, as I mentioned, that the glaciation occurred in the Tibetan Plateau around this region. This the green. This color is the glacial stage, and this the green is the interglacial stage. What we can see that the erosion of the mountains largely correlated with the interglacial period. So because the ice melting causing denudation of the mountain, and then this supply of sediment into the Qaidam Basin. Compared with the prevalent contribution, as I mentioned that it's only a small amount contributed from the Altan Basin. So this Altan Basin mainly occurred in the early stage of the simulation, but for the late stage, it's remained less than 20%. But initially, it's accounted for 50% because as I mentioned during the Qaidam movement B, there is a rapid uplift of the Altan mountains causing deposition. But for the other mountains, like the Quinlan and the Chilean mountains, the contribution since 2.2 million years, it's roughly half and half, around 42% of the contribution. So through this simulation, we can actually really separate the contribution from each mountain ranges, and also we understand the climate control on the sediment, on the denudation and deposition of this region. So this diagram really sum up all the simulation results that we have done so far. So to conclude, so the geomorphic evolution and the denudation of the Qaidam Basin and surrounding mountains has been quantitatively constructed, as shown in the animation. So we find that both tectonic uplift and climate change have exerted significant impact on the denudation and deposition process, the rate, and we can quantify this. The impact varies primarily due to the differential uplift range and also the differential rainfall caused by different geographic locations and the topographic pattern. So mainly, as I mentioned, that the polar and subpolar climate setting. As I mentioned before, the sediment contribution, the prevalence from the Altan, East Quinlan, and Chilean mountains are roughly around 14%, 43%, and 43% respectively. So this actually have shown that such badland modeling can be used to understand the tectonic evolution history of a particular basin. I hope this will be useful to you when you study in your region in Pakistan in a similar setting. So this actually concludes my talk. Thank you. Any question, please?